Okay. I think it's working. So we're good. Okay, so before we proceed, let's talk about what the hell this is. Can you see any of that? No.
Can you make it so it's on top?
Yeah.
Cool. Okay, sorry about that. Sorry for the technical difficulties. Yeah, welcome. So this is the Tour of Scala lecture series. This is the first of probably 5 in total. So a little about why this exists. I'm from Team Megaman in Identity. We have a bunch of services in purely functional with Scala. They are notoriously difficult to contribute to. They're in quite a, it's written in a very esoteric way. What this is it's a way of teaching more people about how our code bases are written, and we're doing that by re-implementing all the primitives that we use to build those services. So, in terms of what we're going to be covering, we're going to be covering this kind of section in this part 1. Part 2 is probably going to be this. Part 3 is going to be this. Part 4 is going to be this. Part 5 is going to be that. So each thing, I've done it in an order that each thing kind of depends on each other, but also kind of justifies their use. What we're going to be doing is we're going to be starting with something that kind of works, and we're going to incrementally get to something better. And I'm going to present this in a way that isn't like, here's this thing, here's how it's going to be used. We're actually going to do it the other way around and be like, this is what we use it for. This is something that we've actually, we do use it in prod, we do use it to do certain things, and then we're actually going to investigate how it's built. So you kind of actually know what's going on under the hood. So when you actually come to if you ever come to a Scala code base in the future at some point in time, your mind just doesn't explode. So in terms of actually beginning, let's do it. Tell me if you can't see anything here. That's a bit better. Okay, can everyone read this text? Cool. Okay, so first up, if you don't get anything, please say something. My job isn't here to finish the talk. If you want to spend time discussing some sort of topic, hit me up. But if you don't say anything, I'll assume that everyone has understood, and I will keep going. Yes?
I can't see anything because the background's probably too black. It shift to a white background.
Okay. That might be interesting. Oh, that's pretty better.
Yeah.
Yeah, okay, that's much better. Awesome, cool. So, let's begin. So, polymorphism. We're going to get to this in a second. So, what is polymorphism? Effectively, we've all done this in first year uni. We have some supertype, we have some two subtypes, and what it allows us to do is it allows us to cram 2 different types into the same function to exploit some sort of common shared behavior. In this instance, it's sound, right? This is subtyping polymorphism. We've all done this at some point. Now, there's something I'm going to show you later on, and it's called ad hoc polymorphism. And it's only you can only do it in a few languages, but I want you to keep in mind what we're going to do is we're going to build up the structures that are necessary in order to do this thing with ad hoc polymorphism. And it's a completely different mechanism to how this works. It's not subtyping. These don't have to extend from the same type. We're going to see how that works. So this works. If I make sound, if I call make sound, it's going to meow. If I make sound, it's going to woof. Right? Make sense so far? Cool. If you don't get any syntax, by the way, just ask me about it. These are our class declarations. Here's our interface. So the next thing is, the really interesting part about subtyping polymorphism is if I had some third-party type, I can't in any way make this work. I either have to extend rabbit, I have to extend rabbit myself. That's the only way I can do it. I can't go to this there's this rabbit in some other external package. I can't add some sound to it. It's not possible. I have to extend it, and I have to override it. We're going to keep that in mind. We're going to think about why that might annoy us, and if there's a way around it, and what that might enable in the future. So, first of all, Scala, Scala's pattern matching. You might have done this in Python. You might have done this something very similar in, JavaScript. For example, here's 1 in the first position. Here's 2 in the second position. We can unpack X and Y by pattern matching on that. We can also pattern match. Here's a cat. As you can see, cat has a single parameter name. We can unpack that name by using the class name, as you can see here. Another thing what we can also do is, given some type of animal, we can what's called pattern match on that animal. And then we can, it's almost like a fancy switch. So what we can do is we can switch on the type of this animal, and then we can either say if we saw a dog, we saw a cat with name N. In this case, we've bound the name to N, and in this case, we've cat matched on a dog, and we said we've seen a dog. And then, for example, in this case, it will say saw a cat with name Boris, because this entire thing is an expression that we bind to animal match. Does that make sense? Cool. We can also pattern match on different kind of numbers. In this example, this one matches on literal. If that was 1, we take this branch. If this was 2 or 3, if this was 2 or 3, we would take this branch. If it was, say, 8, it would take this branch. And if it was none of those, it would be, the result would be don't match anything. As you can see, in this case, it's matching with guard code 5, because that's 5. We can also pattern match with things like regexes. For example, in this kind of situation, we have this EFG, and then we can use this pattern that we've previously declared. We can pattern match with the regex to extract out some C, and then, as you can see, that will match any occurrence of A, B, and C in order, and then it will say capture group. Cool. Brilliant. And here's the one last instance, which is called, what's called the pattern match binding syntax. So what we can do is we can pattern match on this. We can extract out our 1, we can extract out our 2, but we keep the original tuple around here. And so as you can see, matching, destructuring tuple, keeping the original bound state. And yeah, so that's what it will bring over there. Cool. So, as you can see over here. Cool. So that's pattern matching. Did everyone kind of understand what's going on? It's some nice kind of syntax for, like, rather than using bunches of ifs and checking whether things are of certain types and certain fields, we can kind of merge them all together into some kind of like fancy switch. So next thing is scopes. Anything within a curly brace, as you can see here, curly to curly, that's a scope. So the last thing in this scope, that's what this that will be bound to this value, because it's the last thing in the scope. And as you can see, that will be shit. But I'm just going to copy that. That's what it's going to print. So that's kind of effectively a scope. And so that's an expression. So there's a bunch of different ways to play functions in Scala. Do you want me to explain each one? So yeah, for example, this one, its definition, text-2 parameters, it returns a single value x plus 1. In this one, it does the same thing, but its return value is a scope, where the last thing in the scope is x plus 1. This one is not so much a function, but a value with an anonymous function bound to it that returns a scope where the final value is x plus 1. This is exactly the same syntax. In fact, that literally desugars to that. It's a nicer way of doing it. You might see me do this later on. There's lots of different ways to declare functions. And this one, just don't do it. I'm so sorry. So what underscores do is, as you can see, you have this x and you have this y. Underscores are anonymous names of those parameters. So this will literally desugar to that. So the compiler is taking the last thing and turning it into this one. Yeah.
Can we try to ask IntelliJ to add the type in the function definition so that maybe it can be helpful? Yeah.
Yeah. So this is a function. No, why? That's not correct. That's this.
I'm sure there is a shortcut in IntelliJ that does that.
Sorry. Live coding, it's hard.
And you just turn on seconds.
There we go.
That's it.
That's it. So this is, it's a function that takes an integer and returns it.
And I assume the other two functions up there are also the same.
All the same. Wait, go. Next thing, carrying. The Scala is weird. You can have multiple parameter lists, not just one. So in this example, this is an add. It takes one parameter list and another parameter list. And because it has two parameter lists, it means that in this situation, you call it with one set of parameters and then you call it with another set of parameters. And here's that. This is another different version. Here you can see that this, if you've written some JavaScript, you've probably run into this before. Here is an anonymous function returning another anonymous function that returns a scope that returns x possible. And so those are effectively the same thing. What's really useful is that it allows us to partially apply a single parameters. So this can initially takes two parameters, but I can apply just one parameter and I can make an add tree. And here, as you can see, what is interesting is Scala provides a utility, well actually, I'm confusing myself. What does carry do? Ignore that, I've forgotten. Let's not do that. Shit, but what does carry do? Sorry. I wrote this a month ago.
That's it. That's the one.
It's carry versions. Oh, okay, cool. So remember this one? What it does is it has one parameter list and returns an integer, but it has two parameters. What carried will do is it will transform something that has one parameter list of n functions, and it will turn of n parameters, and it will turn it into n parameter lists of one parameter. So we'll split them all up, so you can progressively apply each and every one. And as you can see, I've taken something that took two parameters, I've carried it, so now it only takes one parameter at a time, then I've applied that next parameter. And so now we have an add for function. And then we have a way of going back the other way around. So this is a function that takes an integer, and then returns a scope. Now this is a function that takes two integers at once. And in fact, we can type annotation, as you can see, it takes two integers at once and then returns an integer. Cool. Everyone follow so far? Next thing, you can call Scala functions with zero parameter lists. So we have many parameter lists, we also have zero parameter lists. So here's a function here that has no parameter list. And we can call it like this. In fact, it will actually not print anything up until that point. It has not evaluated yet. And then when I actually use the name, now it will actually start to print things. Cool. And then here's the last thing. This is before we're going to start to do something interesting, but I need to get this out of the way before I confuse everyone later on. This is the boring bit, I'm so sorry. But we need to do this. Scala introduces the concept of strictness. For example, here's a value and it's strict. What will happen is when the program runs for the first time, it will evaluate everything. So what will happen is this will be run. And it will log. This is a lazy val, which means that it will internally will only be evaluated if the program uses it. Because we don't actually use lazy val anywhere in this program, this log line will not pop up. And the return value is lazy val return value. And so here, this is effectively the same thing. It's a lazy definition. It's a function that has no parameter list, works in much the same way. And we're going to come back to this later.
Remember the value after it's evaluated first time?
No. Cool.
So therefore, evaluates every time, right?
Yeah.
Instead, lazy file is like a synchronized block.
Yeah.
It translates and synchronizes in Java.
Okay. So we're going to come back to that later. That's actually a fourth lecture thing. But let's proceed. So this is
when you compile to the Java language, it actually translates into like a synchronized inside. So it will actually put the value inside of the JVM object.
So it's synchronized. I don't think it transforms to like if you're talking about the synchronized as anyone.
Oh yeah, it is not, but it will basically execute and
sorry. Okay, so this is the essence of Scala. Right. This following little section you're going to see in no other language. It's completely unique. If you can understand this next 20 minutes, you're in luck. So, for example, Here's a parameter list. Here's a function that has two parameter lists. It has one parameter list that takes no parameters, and another parameter list where one of the parameters is marked implicit. And up here we have a value that is also marked implicit. You're thinking, what the fuck is that? So what is really interesting is when I call this function, it will scoop up this and auto-apply it. And what we can see is we have a feature called implicit intelligence. And what you'll see is, ignore the generates, because that's my pretty printer doing some fancy things. So you can see what it's done is it's taken this implicit string and it's auto-applied it for us. We've filled one parameter list with nothing, and then it's taken this implicit string and applied it to here. And so when we actually call this function, it will print implicit string, because that's what it does, is it takes the x, the implicit string, and here's the implicit string, and it will print it, or return it, right? Let's sink in for a second. If you have any questions about what I just showed you there. So here's something that's actually like a good way of using it in production, right? Here's like your 3 layers of your application. You've got your controller, your service layer, and your data access layer, right? And hypothetically, you pull some authorization header out of your controller level in your application. You figure out what tenant that is. And then when you call the service layer, you thread that tenant info implicitly throughout the application. As you can kind of see, when I call service layer, I only have to supply one parameter, because it will take this implicit tenant context. And if I show you my implicit hints, you can kind of see what will happen is we'll apply the tenant context. And then when I call in my service layer, here's my context. When I call data access layer, it will apply my context for me. And when I call my data access layer, it will apply my context once. So it's a kind of way of threading some value through multiple function calls, but it will do it all for you automatically. And you can see it's type directed, because this one is asking for implicit string, so we'll fetch an implicit string. And here this is a tenant info, right? And so because the implicit is tenant info, it will recover the implicit that is the tenant info. Cool. Everyone following?
I have a question. I assume it's like ordered, so like what if you have multiple implicit variables and then...
If you have multiple
uses
implicit
one?
variables of the same type, you're going to compile. It will say there are conflicting implicits. I can't
So it doesn't like override, a new one doesn't override the previous.
It will be like, these are ambiguous.
Does it work if like you have an inner scope and then you have a new implicit?
When you say in scope. So if you have one implicit in one, like a larger scope, and you have a more specific scope, no, it'll freak out again.
What if you have 2 implicit strings and then a function takes 2 implicit strings?
It's not gonna work.
It's not gonna work either. Now, there's something I haven't shown you. We can actually explicitly supply that parameter. That compiles, right? The service layer has 2 inputs, it has 2 parameter lists, and here I'm taking an input. I'm explicitly applying an implicit parameter. Which is interesting, Sometimes in the case where we can't disambiguate between implicits, we can like panic and imply it. So, next bit. Now this is the essence of the fucking language. You cannot show me sorry about that. Ross is gonna love it. There's like 4 languages that can do this. It's not many. Like it's really hard to do. So what's happening is it's type directed. We have 2 implicits, they have 2 different types. This is a function that is generic over T, and the implicit parameter we recover is that T. And so what we can do is, depending on the type parameter we supply to this function, it will recover a different type. Now remember how I said back at the start of the talk, polymorphism, depending on 2 different types, we want to do some different thing. This is literally polymorphism without subtyping. Boolean and integers are 2 different types, but based on some different type parameterization, we can do 2 different things. Yes.
Isn't this like C++ template parameters?
Effectively, yeah, but much scarier.
Could that, like if you were passing raw implicitly, to a function that took a Boolean,
Yeah?
would it like be able to infer that type parameter? And you could just say like
Yes.
function for implicit.
It would be able to infer that type. Because yeah, you can go val x Boolean equals raw implicitly. That will apply. In fact, we can go show implicit yes, and it will have Boolean implicit Boolean. Ta-da! That's pretty cool. You know, that's really, really funky. You know, you can actually figure out what implicit it needs to recover based on type vectors. So, here's the scary bit. You can recover them in a higher kind of manner. Now, this is a list of integers, right? And this is an option of integers. An option of integers is, for those who don't know what option is a list of either 0 values or 1 value. Is the 1 value form and the 0 value form is called none, right? Makes sense, you know, rather than have n many values, it's 0 or 1, you know. So here what we can do is, based on the type we asked for, what it will do, so for example, we'll go hkt implicitly list. What will that will become list. It will apply int to list, and then we'll try and recover list int. It's taking the list part, smushing the int part together, and now it's going to try and get the list int. Cool. Does that make sense? And then the same thing happens for option. Cool. So, what is really interesting is we have this type called id. What id does is it takes a type parameter and it returns that type parameter. So, we're going to do a very similar thing from before. So we have some higher kind of type parameter, and then we have another type parameter. And we're going to get that higher kind of type parameter, and we're going to take that type parameter, we're going to smush them together, and then we're going to try and recover it. So here we've got this one. We get list and string, we smush it together, and we try and recover our list and string, which is here. Here we have our list and Boolean, and we smush them together, and we try and get our list of Boolean, as you can see. And here we have id, and we take id, and we smush it together with string, and we get string. So we recover the implicit string that I showed you before. Did that make sense? So this is kind of like a type function, you know, taking a type and returning a type, where list takes a type which is string and returns another type, which is list string. Cool. It gets scary. Our implicits can have generic parameters. Now this is kind of, you're like, why am I telling you this? In lecture 3, you'll figure out why that's the case, because it gets kind of hairy and you'll be like, well, what the hell, what are you doing, Max? Why are you showing me this? But, for example, this is, for some generic option, for some option of A, it can be an option of in, be an option of string, whatever the hell it is, we can recover an implicit, right? Because in this case, this implicitly, it looks for an option of dog. It finds an implicit of option of A, and it's like, well, I can make that an option of dog because it's a generic parameter A, and then I will recover it. And as you can see, it recovers another number. That was a lot. Does that confuse anyone? Peter, I can see you scratching your
No,
eyebrow.
I'm just like this is a test best on my 322.
Where else, sorry?
empty the naming.
They will find.
Oh, empty option, empty option, empty option. Yeah, of course. That was Scala bug before. Cool. So, implicit objects. Objects can be implicit as well, which is fun. This is like an object, like floating off in the distance, like somewhere in Scala, and it has static fields. So, yeah, these are static fields. They're accessible from anywhere in the program. At any point in time, what we can do is we can go static cat and we can call sound. And we can implicitly recover this static cat because it's of type cat. We're allowed to do that. You know? It extends cat, it's a cat. I can recover that type, you know? Why not? Cool. Okay, we're going to brief interlude. Syntax extensions. Has anyone used Kotlin? Cool. We've all done syntax extensions in Kotlin. This is how you do it in Scala. Put an implicit class. It shouldn't be called implicit class, but it is. And so what an implicit class will do is given some type of int, it will wrap itself around it, and it will give you this method. And so now what we can do is if we import it, because it's kind of good practice to kind of like put these kind of classes inside some other objects that they don't like with the namespace. We can now call increment on this like 5. It will work. Pretty cool. Awesome.
Can we show the implicit hints there so that we can actually see the implicit class in action?
Implicit hints. Hint extensions. There it is. There's our class that's wrapped itself around this type, which is kind of cool.
What does this generate mean?
It's sort of a log, the pretty great actually. So, remember that sound that we had before? We had that, oh sorry, up here. We had this animal, we had this dog, we had this cat, and they had sounds. But we wanted to add a sound to rabbit, we couldn't do it. It makes us sad. I'm going to show you a way you can do that. And it's a bit spooky, but we'll get to it. And I'll show you what it looks like. In the end, what it looks like is this. I can call all these 3 functions. And as you can see, it's actually compiling. And that's the function that actually, wait a second. What the hell? Oh yeah, okay, cool. And this is the function that is allowed to use both dog, cat, and rabbit. We're going to look at why that's the case. So, how it works. First of all, we create this class called sound, right? Or this interface called sound. And what sound says is for some type A, given that A, I can give you a sound of string. That's what semantically I intended on the. That's not just how it works, that's what I'm saying how it works. And so what we have is we have this thing called a sound id extension. And it wraps itself around any type A. And what it will do is it will say, when I call this sound extension, function, what it will do is it will recover some instance, some implicit that is floating around in our program of sound of type A, and it will recover the sound. And here is an example of those instances. So for example here, this is trait sound dog. And it is of type sound of dog. And it has a method on it that's woof. We have a sound cat, it's of type sound cat, and sound. And we have sound rabbit, it's of type sound rabbit, right? And then we make those implicits. So here we have here's a variable, it's of sound dog, we have cat, sound cat. So these are implicit. These are all, there's some, these are all available if I want to. What I can do is if I really want to, I can go like this. I can go implicitly sound cat. And that's going to be, it's going to take a cat, as you can see. And then it will give you the sound that a cat makes. That's something we can do.
So am I right to assume that this is actually kind of like deferring the responsibility from the object, say cat, dog, rabbit, to something that can prove that you can actually make a sound?
Yeah, that's exactly what it is. So here's that function that gets that sound out. So what it does, it takes some generic type A, and then it will try and recover the sound instance of that A. And then once it has that sound instance, this sound extension will take that instance, as you can see here, and then we'll call that sound. So what we can actually make it look like this. probably a better option. Yeah, right there. Cool. There we go. That's much nicer, right? Then it will actually call this out. And so now what we can do is we can call this function and this function and this function on these three things. And as you can see here, when I call this function, it recovers the dog instance. When I call this function, it recovers the cat instance. When I call this function, it recovers the rabbit instance. And that instance is getting flown through to the sounded extension. And when the sounded extension gets that instance, it gets the sound associated with that instance. That's cool, you know? That's really, really, really kind of cool. You know, we've done polymorphism without subclassing. And so here, there's this function. That syntax is a bit ugly. Why do I don't want to say implicit instance sound of A, right? Ugh, disgusting. What Scala will do is we'll desugar this literally to this. You can say, for some A that has sound, take the A and call sound on it. You know? That's kind of nice syntax. And it's literally transforming this to this. And as you can see, when I call make sound generic requirement on a dog, it will have some hints. There we are, we have the dog instance. It's recovered the dog instance. Okay, everyone understanding so far? Cool. Here's this class, it has no sound. What will happen is if I try and call this function with has no sound class, it's going to go, no implicits found for parameter instance sound, has no sound. It's like, what the fuck, I can't do that. There's no implicits in scope. What I can do is I can come along and I can actually write one if I wanted to. I can add my own behavior to this class even though I might not control it. I can go, you know, trade has no sound, and extends sound has no sound, you know. And then we can add a sound. That's pretty cool, you know, that's really useful. So, making sense so far. So that's okay, let's use this for something kind of practical. I have a person, it's me, right? New class. And what I want to do is I want to be able to do this. I want to call an encode method and it's going to spit out some JSON of who I am. Right? That's something that we probably want to do at some point, right? And we want to just add this behavior to this arbitrary class. So let's do it. We have an encode trait. And we can say for any A, if you give me that A, I can encode it into JSON. I have some syntax extension. You're going to see this pattern a lot. Typecast pattern, because it's boilerplate. We actually have macros that provide this for us. Take some A. If that, we have some A, we recover the encode of A, and we get the encode method, we cram that A in, and we get JSON out. We have instances. We say for encode string, it takes a string and it quotes it. Encode of int, converts it to a string. Encode of boolean, takes a boolean, converts it to a string. Encode map. What it will do is if that map is a map of strings to JSON, it'll do some kind of fancy stuff, right? Nice and fun. Nice like little utilities. And then we declare their instantiation. We have an encoded string, we have an encoded int, we have an encoded boolean, we have an encoded map. And now this is the cool thing. I can add my own custom encoder for person. But I don't declare the behavior in the class, I declare it external to the class. So I can add this, I can encode types that I don't control. And so here we make an encoder person, we override the encode method, takes a person, turns it to JSON. And then here what I can do is I can call encode on strings. Because that's what I declared before. I said we can declare, let's see, give it a second, encode in extensions, and it's recovering the encode string instance. And so then, now that I've declared this encode person, I can now encode myself. That's what it spits out. You can see here, encoded extensions that allow that encode syntax to work, which recovers the encoded person and then spits out the string. Cool. Awesome. Any questions? And here's another function. Here's a function that takes some A that can be encoded, and then what it's going to do is it's then going to encode. And if we really want to, we can still recover the instance. So here's the instance, we've got instance, encode, right? That's the actual thing that does the encoding for us, plugging around. Because when we have an A of encode, that's desugaring to implicit instance encode of A. And because it's in scope, we can implicitly recover that encode of A. Cool. Any questions? Dot? Okay, I'm gonna get a drink because my mouth is there.
Nice one.
Okay, how long do I have? Ah, we still have 50 minutes left.
Our meeting, so
Okay, cool. So, that's part 0. That's kind of the most primitive parts of Scala done. That was 500 lines. Here's part 1. We have 1,700 lines. No, it ends at 4. Don't worry, we're all good. Okay, so let's do some interesting stuff. Remember how I said option was it's a list of 1 or 0 elements. This is how it's literally declared. So it's saying that an option of sum type A, it's either a sum of, a sum of A has one value A, and it's an option of A. Yep.
Why does option have to be over?
Doesn't necessarily. And so here we have a none. None can be a none inhabits any type, we would say. So if you have an empty list is, for example, it's a list of integers, it's a list of strings, it could be anything, right? And so we say this empty list, this empty option, it's an option of nothing. It can be anything. So what is interesting is we commonly in functional programming languages we use this option to encode the idea of null. We don't like nulls. Nulls are bad. Nulls give us null pointer exceptions. And by using this very special type, we have ways of preventing null pointer exceptions. And so the classic example is, say we have some class family member. Those family members have ages, but they may or may not have mother or father, right? You can have 0 or you can have 1. That's the list of stuff you get. So, for example, I make a family tree here, right? And I make a family. So we have this list of family. We have a list of family members. We have nana. We have great granddad. Yeah, you can see what's going on. Yeah. And so but I had this arranged in some nice, pretty tree before the format told me to go fast. So we can have this function. We say get parents' ages. We have a family member. We get their parents, and we get all their ages there. Remember that underscore I showed you before? That's like a nice little way of doing this. Right? XH. Right? Yeah, cool. That's literally this. It literally distributes stuff. Cool. And so now we have a new function, get mother's age, right? What it's going to do is it's going to take a family member. It's going to get my mother and it's going to get their mother, sorry. It's going to map over that. And what it will do is it will map over that list of 0 or 1 and it will get the age out. Right? Cool. Did I say anything weird?
No,
Okay.
it's funny how you say, oh yeah, no, get their mother.
Okay, so as you can see, get parents' ages, 55, 56, get parents' ages of grandma, nothing, because the parents are dead. Get mother's age, I'm sorry,
Both of the mothers are dead.
their parents of grandma are dead, I'm afraid. So, sorry about that.
It's become such a depressing.
And so get mother's age, some, but in this instance, as you can see, grandma doesn't have, grandma actually seems to have a mother. Who doesn't have a mother? Oh, granddad doesn't have a mother, granddad. And you can see that's none, right? So we've tried to map over, we tried to get their age, but they didn't have granddad, so we're going to return none. So we're kind of propagating that thing. If the thing exists, if the I've done a really bad job of this, sorry. If this is a sum, we're going to return a sum of it. And if this is a none, we're going to return a none.
Why do you have to map over an option?
That's how we convert the option.
You can't just do like mother.age, it'll return none or some of value.
No, it will return. So if you do mother.age, what you'll find is that will be, like, what is mother? Mother is a type option, right? Age is an on option. We have a map function on option. And you'll see that that map function, what that map function says here is it takes, you can't really see that. But what it's saying here is the type is that map takes a family member to some type of B, and it will return the option of B. And so this function, it takes a family member and it returns the age, which is an int. So we'll convert this option of family member to an option of int. So it's getting the age out. And that's in much the same way out this.
What exactly is the sum of 55? Is it like 55 ones?
No, it's like
So it's like, what was that, sorry?
What is the sum of 55? What is
No, when sum is like, there's one value. It's
Okay.
like, it's in the option case, it's like, there is a value, there is an age,
Okay.
it's 55.
Sure.
Otherwise, if there's no age, none. Yeah. So, let's make a new function. Get ages from list. What this will do is, so we have a list of family members and we want a list of age. So we go family member, we map over, we take a family member and we get their age out. Here we have another function, get age from function. We have an option of a family member. That family member may or may not exist. And we get an option of age. So if the family member exists, we get their age. If the family member doesn't exist, we return none. It's a family member, they were none to begin with, and they're none at the end. Cool. And so here's some instances of that working. Right. So get age from list, takes a list of ages. Oh, it has a family, we get a list of ages. Grandma doesn't have any parents, we get a list of no ages. Son has a mother, so we get their age, some age. But in this case, grandpa isn't alive. What was it again? Grandparent. Yeah, grandparent. Didn't have a mother, so when we try and get their age, we get none. But you can kind of see that these functions, there's kind of something very similar to these, right? It takes some list of family member and transforms it to a list of people. This is an option of family member and turns it into an option of people. They both call map, and then they take the thing, they convert the family member. And then this one, we do exactly the same thing. We take a map, family member, and we convert it to it, right? So there's something common, right? We don't want to keep writing this function over and over again whenever we want to get an age out, whether it's a list of things or whether it's some family member that may not exist. So, like, yeah, that's what we want to do. We want some get age function. It takes something,
A containery type.
containery thing, that contains family members and gets their ages out, whether that's a list or an option. I don't know what that is. We want to call map on them. We want to get their age out. That makes sense. So here's the thing. Here's that thing. This is. I'm going to show you a way to do that. It's called functor, and that's this functor says, this trait functor says that there's some containery thing that takes some other type. So whether it's like maybe a list has some other type, it's a list of ints. There's this function called map. And it takes that containery thing, and it takes this function that accesses the inner value inside the containery thing, like that mapping function, the thing family member to family member range. And it will return you that containery function that has had the thing converted. And the syntax is much the same way. This is, we're getting bored of this kind of stuff. It covers the instance, wraps itself around some containery thing. Now it has a new method called map, recovers the instance, and then it calls the map and with the function, etc. We've seen this all before. But let's look at the actual instances. This is the kind of the meat and potatoes of the thing. It's a functor list. And functor is functor of list, what it does. There's a map function. It takes some list of A's, and we have some function that takes those A's and converts them to B's. And the return type is that list of these, right? And this is our map function. Let's not implement that. It's kind of spooky. But what it's doing is it's going through the list and it's rebuilding the list with all the things inside the list converted with that f function that we've provided. And so now we have option, the list that has 1 or 0 values. If the list has got 1 value, fuck off. If the list has 1 value in it, we unwrap it, we apply our function, and we rewrap it. Otherwise, we return the empty list. And then we declare our instance. And here we try and use it. And it works, as you can see here. Here's a function. Look at age. It takes some f. Sorry, it's generic over some f that takes some other parameter, where it can recover an instance of that, a functor instance of that f. So as we saw before, we had this list. It takes another type. We say this is a functor of list. Here's this functor of option. Option takes another type, like an int or a string. And then what it's going to do is it's going to recover. That's going to de-sugar to this, right? Come on. It's actually really laggy. Did you know that? When you have that recording?
Oh, yeah.
That's what it's going to de-sugar to. And it's going to recover that instance, and it's going to pass that instance into the map extension. And it's going to call map.
Let me show the disciplines here.
Yes,
Very
we can.
exciting. Hey.
As you can see, functor, functor extensions, which is the map function up here. There we are, there's a map function. And yeah, see, get age, family, it's recovered the list functor instance. Here's it's recovered for the option instance. Pretty cool, right? I've added this. I haven't touched the original implementation, you know?
So does that mean that if I were to implement a functor of our, just making things up here, but futures or eithers, you can actually do it too?
Yeah. Pretty fun. Cool. So I'm gonna. How much time do I have? Okay, 35 minutes. I have 35 minutes. Okay, cool. We might get to moment. Has anyone got any questions so far? I need everyone to understand what's going on before I proceed. It's going to get hairy very quickly. Cool. Grand matriarch. I want my mother's 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 time. So I get my mother, and then I get my mother's mother, and then in this scope I get now I get my grandmother's mother, now I get my great-grandmother's mother. And it actually works, you know. I got this 103. But yeah, we can get it out, you know. We're able to access the age of my grandmother, you know, with use this map function to get my mother. And if I get my mum, unfortunately I don't have a great-great-grandmother alive, so let's go some number. So it didn't get value out, you know, wasn't able to get that age. And we can do that with this one, get all great-grandparent ages. So I can get, then I can get their parents, and then I get their parents' parents, and then their parents' parents' parents, and then I get their ages, right? See? And we can get them, 103, 104. It works. Kind of. There's a bunch of lists in the way. But we get the values out. Now I want the sum of the person's parents. Sum of the person's parents' ages, right? So I can go mother, I can that mother, then I can go father, I can that father, and then I can get the age, and I can get the age, and I can get the, right? Sum all the ages, right? And I get option in. So in the case of son, we're actually able to add up all the ages, and that in the case of mum, because there's no dad, well, her father isn't alive, we go summer. So we're able to do like safe computations on null values, right? If the values don't exist, we get nuns. If the values exist, we get the actual values out. But it's kind of dumb that we have, like, when we do more computations, we get like these layers of types. Like we've got 3 intermediate lists here. That's a bit ridiculous, don't you think? Like, yeah. And here, right? Some, none. It should be an empty list, right? I wasn't able to get the age out. That should be get grand matriarch age, option in, right? And if I'm able to get the grand matriarch age, I should have a sum of 103, otherwise I should have a none. And I'm saying this because I want it to be that way. It's not because it's the correct way. I want it to be like this. This would work, but it's a bit dumb if we do it like this. We want something that when we do multiple layers of computations, when we do a map and a map and a map, we're going to flatten it down. You know, we want it to be a listed in, an option in. We can do that. We can write this function called flatten option. What it does, it takes 2 options and it flattens it down to a single option, right? So remember how before, if it's like a sum of a none, it's a none, you know? The value, we couldn't get the value out. So we go, if it's, but otherwise in every case, if it's a sum of a sum, it's a sum, you know? You're able to get the value. So, for example, this one, that should be a sum of 130. And in this case, this should be a none. So we say, case sum A, it's a sum of that. Otherwise, it's a none. Cool. And so what we can do is we can rewrite that version, get great matriarch age flatten, right for the name. And so as you can see, we map, and then we flatten, and then we map, and then we flatten. And then we get an option in at the end. As you can see here, get grand matriarch age of sum, we get sum of some age. Sorry? Surely there's a better way. Surely there's a better way, you know? And now we have get great matriarch flatten none. We weren't able to get it, but it's now just a none. It's not a sum of a none, it's a none. But we weren't able to get the value. You know, if you're using Kotlin, you get an age or you get a none. Here we've got an age and we've got a sum of age, and here we have a none. So it's accumulating these values. It's compressing them. You know, map, flatten. What if we did them both at once? For every map, we do another flatten, right? We need to chain our maps. We want to do a map after a map after a map. We have something that's doing a flatten, like a flat map. Hey, it's a flat map. Hey, it's a flat map. Don't ignore this line. Just pretend it doesn't exist. See that? It's gone. Anyway. So,
What's that line?
part 4. So, we have this thing called monad. What monads are is they're functors, but with more stuff. And so, if functors have map, monads have flatten. And because we have map and then we have flatten, we for free get this thing called flatten. Hey, that's nice. So, remember how before I was implementing this flatten option thing, let's just say that anything that has a flatten method is also a monad, if it also has map. And we're gonna look at that in a second. So, before I actually show you the implementation, let's look at how nice it looks after we've added flat map. Hey, look at that. Look how pretty it is. The reason we invented monad is to make this shit look pretty. Don't let anyone tell you otherwise. It wasn't because you needed to do side effects. It wasn't because you needed to do all these other fancy things. It wasn't because you wanted referential transparencies. Because we wanted it to look pretty, you know? That's all it is. It's making it look pretty. Just remember that. When people start talking about monads, we want it to look pretty, you know?
Beautiful.
It's beautiful, you know? So now, our mother, when we want to get the grand matriarch age, instead of having this, you know, weird kind of pyramid thing, what we do is what we have mother, flat map, mother, map, to get the age right at the end. Look at that.
Why is the last one map?
Yeah, good question. Age doesn't, so we're going to look at what flat map, the function actually looks like to answer that question. So, if we come back, so, ignore that one. These are the things you need to implement for monads to exist. First is the flat method, because we already have the map method up in the front. And what it does is it takes two layers of anything that you call a monad, for example, a list and a list, and finds it down to a single list. Maybe it's an option of an option, like say some number, some number. Yeah. Smush, right? That's the fun method. And so what we can do is, here's that bullshit we saw before, bunch of these syntax extensions, you get your A, you get your instance, you run the function. You get your A, you get your instance, you run the function. You get your A, you get the instance, you run the function. So, there, cut to the chase. So, let's look at this. Here's the instances for some things that we're going to call monads. First of all, we're going to call this monad. We have this extra function called point, and I'm going to come to it in a second, but unfortunately I have to show you now. So what fun? And that fun is an important one. So fun, it takes two lists, and it smushes it down to a single list.
When you say two lists, do you mean like a list
So,
within a list?
two layers of lists, and it funs it down. Here's the implementation. Really scary. Strict, optimized, flatten. Actually, it's kind of nice. Oh well. Anyway, I could have inlined that, but we haven't. And for option, what it does is it takes our two layers that we saw before, and it flattens it down. Smush. Otherwise, if it's anything else, it's a null. That was that one I showed you before. And we also have this extra function for monads called point. What points do is it takes some arbitrary type A and it puts it inside the monad.
Just for the avoidance of doubt, so it
Yeah.
might be useful in a future talk to actually inline that method on line 254, because that flatten method column there is not the one that's within, it's actually the flatten method on the list object.
It's the flatten method on the list object. Yeah,
Because it already implements that one.
yeah, that's exactly right. Yeah. So point, for example, point, what we'll do is it'll take some type of A and it will put it in a list. So if you go, if you look at my syntax extension, what it will do is for some type A, it will recover the instance. For some type A, there's now a point method on it that will run the point function. So for example, 5-point list will equal list of 5. Ta-da! That's what it will do. For the option example, 5-point option will equal sum of 5, because it's the one element list, right? It's going to take somebody and it's going to put it in the modes. We're going to see why that's interesting in a second. And so these are the two methods that we need to implement to create modes. We need to implement point. We need to implement flatten. And if we implement flatten, and because we already have map from the previous one, we get flat map. Flat map's very simple. It's a map, and then it's a flat map. Quite simple. It's right there in the name. And so what flat map? It has this kind of signature. It's saying that, say you have some list of A's, like some monad of A's, right? And you have some function that takes some A and returns another monad of B's, you now have a monad of B's. And here's this in actual practice. Here we have some person's mother, and then when we try and get that person's mother's mother, you'll see here that there is a list of family members. Oh, sorry, that's an option of family member. This is a function that takes a family member and returns another option. And so what it's doing is it's flattening it down. Up here, when we did that, The result of that is an option of family member. So what this was an option of family member. And then this was a function from a family member to an option of family member. And because the map function, what it was doing is it was taking that option, it was taking that family member to an option of family member. And it was giving you an option of family member. It wasn't able to flatten it down. It was making that extra layer. And so what our flat map function is doing is it's getting rid of that extra layer that allows us to chain our calls. That was a lot. We need more examples. Of course we need more examples. Here's another example. Here I'm doing it with lists. We have a member, we have our parents, right? We have a list of family members. We flat map over it. We take that, each parent in that list of parents, and we get their parents. That's a list. That was also a list. If that was a map, that would be a list of family. But because it's a flat map, now it's just a list of family members. We eliminated the nesting. And so what we can do is we can do another layer, grandparents, list of family members, and we'll flatten it down. And then the final map takes this as all of this here. That is a list of family members. We can map over that list of family members and get their ages. That's why there's a map at the end. Because we have our list of family members. We've used flat map a few times to eliminate that nesting. And because age doesn't introduce any nesting, we're free to use map, not flat map.
Just taking that a bit further, so I think David has also a good point there. Why is it a map, not a flat map? Would it then be possible to say, hey, flat map, grandparents age pointed to a list, for instance? Because then you will flatten the list, right?
So this is where the point method comes. Flat map, point, list.
I think the main point is that in that last map, great-grandparent.age is non-optional, so it doesn't need to be a flat map.
Yeah, it's not a list, sorry.
No, it's not.
Yeah. So we're allowed to do this. We can actually make this last call a flat map because what we've done is we've pointed it. So now this is a list of ages. And so what we've done is now we have a function from family member to list of age, right? We're allowed to do that now because that's a flat map. If we didn't have that point, we wouldn't need that list. Making sense? Cool. What's really kind of interesting now is this kind of becomes a lot nicer. What we have is some of age of parents, some age of person and parents. Take a family member, we return an option in. We go mother, flat map, we get the mother out. In that same scope, we get the member, we get their father. We map over. That there is an option. Now that's an option there. Oh, sorry, that's an option of family member. That's a family member. Now we can get that age and that age and that age. Did that make sense? Cool. Okay. So, can you notice something kind of interesting here? In that what we've tried to do here is we've tried to get rid of these triangles. Triangles are doomed. We don't like triangles. They make us upset, you know? And by adding this kind of flat map function, we've gotten rid of some of the triangles of doom. They're less upsetting anymore. Oh, there's less upsetting. But this last one is still a bit of a triangle of doom, right? And the reason it's a triangle of doom is because we're accessing the optional mother here. So this is an option of family member, and here it's a family member. This is an option of family member, and here it's a family member. And we have to keep both of these in scope to finally do this kind of computation right at the end. So we need to do that though. There's no really any other way to make that happen. But what we can do is we can give it nice assumptions. Everything you see on this screen, I'm going to show you, I'm going to scroll down. The next slide literally desugars to this. I want you to take this in. Just look at it, commit it to memory. Ready? There we are. Scala will convert that to everything you just saw. And so now, it kind of looks a bit like imperative programming. A little bit. Not quite. But if you squint, you'll see it. But what's really interesting, so what it's actually doing is, what it's doing is it's going, this thing, dot flat map, parent, that, dot flat map, grandparent, that, dot flat map, great grandparent, and then the yield is a map at the end.
That's really useful. In that case, and if any of those are none, it will short circuit, right?
Yeah.
Computation will just not.
It's the same code. It's literally the same code. It's everything we saw. We saw flat map, flat map, map, flat map, flat map, map, flat map, map. Ready? Flat map, flat map, flat map, map, flat map, flat map, flat map, map, flat map, map. That's exactly like this. It's literally transforming into what you just saw. And the really interesting thing is if we actually show the implicit hints, you'll see what it's doing. It's a second. Oh shit. Work. Okay. Doesn't want to do it. Anyway, yeah. Yeah, IntelliJ is not working for me anymore. But, yeah. Okay. Yeah, that's my luck. But you can kind of see what is interesting is this kind of final line here, that is a father, and then we do this computation at the end. That is that there.
Could you also align it into that full block?
You could actually. You could have been one into it. There it is. There you go.
Could you do it nicer with the equal syntax, please? So have it as you had, and then the next line underneath could be result equals father.map.
Not sure I understand. Yeah, you could do that. Yeah. And so what we can do is we can actually further align this. That was a transformation. That was a transformation from that last section there. What we did is so what we did is we took that last section and we inlined it as a map. And we took that and made that the result. And then what we can do is we can do one last thing, which is we can take this. We can go flat map. Flat map. Flat map. Oh, sorry, I can't do that. It's not working for me. But, okay, does everyone understand what's going on in terms of this for notation syntax? What it's actually trying to do? We're using this kind of notation itself to kind of destructure itself into this series of function calls, where we can actually define the behavior of both flat map and map. Cool? Nice. Okay. Do we want to end it here, or do we want to see a stripped down promise?
For what?
A stripped down promise.
Oh yeah. Can you do it in 15 minutes?
Can we do it in 15 minutes? Nah, everyone's too tired. Okay.
That's true.
Let's leave it at that. Cool. Thank you. Cool.